Welcome back to Greenplum Summit 2020, the Reimagined Digital Customer Conference. My name is Jacques Eistock, and my next guest is Domino Valdano. Domino's a staff software engineer here at VMware Tanzu, and today she's going to cover unsupervised learning using Greenplum and Apache MADlib on really large data sets. Domino.
Hi, I'm Domino Valdano. I'm a member of the same Greenplum team Advanced Analytics as Ekta. She talked to you about deep learning, which is a type of supervised learning. I'd like to talk to you about another large class of machine learning problems called unsupervised learning. Next slide, please. So this is how they both fit into the general machine learning thing. So what she was talking about is image recognition, which is a form of classification, and then regression also falls under supervised learning. And then unsupervised learning can be clustering, it can be other things. The main thing that's in common with all types of supervised learning is you're looking at kind of an unstructured data set, which hasn't been labeled in advance, and you're just looking for patterns of self-similarity within that data set. And if it's large enough, usually you can find this part of it's kind of similar to this part, etc. So next slide. So these are some of the things you might associate with supervised learning. It's kind of the same in the classroom as in AI. There's very clear metrics of like, this image is a tiger, this is an elephant, you got this right or wrong. And you get feedback, you get graded on it. It's sort of like reinforcement learning where you, how you train like a dog or a horse to do a particular thing. Next slide, please. With unsupervised learning, it's more about exploration and discovery, and your goals are more open-ended. There's no right answers. You don't know exactly what you're looking for until you see it. Next slide, please. So here's what the SQL interface in MADlib looks like for our unsupervised learning functions. Pretty similar to the supervised ones. Generally, you'll have a train function and then a predict function. The main difference is that instead of having both an independent variable and a dependent variable like x and y, the input and the output of your data set, you only have an independent variable. There's only the input data. It's not pre-categorized or pre-organized. Next slide. So the first type of unsupervised learning I'm going to talk about is association rules. If you know that a user likes Lord of the Rings and they also like Star Trek, then there might be a good chance that they like Star Wars. This would be like an example of like how Netflix recommendations would work or something. You might use an association rule that says, if you see these two items, then there's probably this item is going to be interesting or go along with them or be in the same transaction. And you could do this for movies, you could do it for music. The classic example is like buying a basket of goods at the grocery store or in your Amazon shopping cart when you check out to see like what other items might you also want. Next slide, please. So here's some of the terminology surrounding association rules. First, you have a set of items, I, and then you also have a set of transactions, which is each transaction is some subset of the whole set of items. And then you have rules. And the rules are of the form X implies Y, where X is both X and Y are also some subsets of the items. And so you just look, where does X show up in these list of transactions, and how often does Y show up when X is there? And for for instance, for the movies case, it might be hard to define exactly what constitutes a transaction. You might just break it up into users and say, whatever movies that user has watched entirely is one transaction. Or you might say whatever they've watched in the past hour or the past week or the past month. Whereas listening to music, it might be just the past hour or something. So you also have support of X is like, what fraction of the transactions does X occur in? And then the confidence is basically how often is the rule true. The lift tells you about how correlated X and Y are. And that's unlike the confidence and the conviction, that's like a symmetric relationship. If they're totally independent variables, then the lift will be 1. And if it's less than 1, that means they're substitute goods. Like if you bought something for Android, let's say, then you probably don't want something for iPhone because those are negatively correlated. And then if the lift is greater than 1, that's when it's a dependent relationship one way or the other. So that's when you would actually want to pick an association rule. The conviction is similar to the confidence, but instead of telling you about how often the rules are true, it tells you about the error rate, like how often the rule is false and how much better you do by imposing the rule as opposed to not imposing it. Next slide. So if you're doing association rules in MADlib, you would start by making a table like this of transactions. And you can see like transaction 2 here had 2 products in it. Transaction 3 and 4 also. Transaction 6 had 3 products. And so you've just got this long table. Next. And then you call madlib.assoc rules and you pass it in a minimum support. So here it's saying the rule has to, or the X part, the left-hand side of the rule has to show up at least 25% of the time. And you say, don't select this rule unless it's at least 50% confidence. And then you can add other conditions onto there. Next slide, please. And since we chose also verbose mode, it gives you like a progress report as it's going through. And it does it iteratively. First, it builds it up with, on the first iteration with just 1 item, tends to go with 1 item, and then it will go to 2 items and 3 items because it's easy to figure it out in that order as you figure out the support and the confidence and all of that. And then it picks which rules and returns them in a table. So here it picked out a total of 5 rules. Next slide. So now let's move to another big example of unsupervised learning, which is clustering. Now there's many kinds of clustering algorithms. I'm going to talk to you about one called Kmeans. So this is another way in which you might find a pattern in a data set that you have. You don't know what these clusters are, but you notice that they're all kind of close to each other. So as long as you have some notion of distance between points in a data set, it could be a multi-dimensional data set. It could be, 10 or 100 dimensions. This is just a simple 2-dimensional example. And you can see there's 4 clusters here. Some noise, but basically 4 clusters. And then in the table, it would just look like a set of points. Next slide. So here are some of the applications that you can use clustering for. Customer segmentation, event locality in like a geospatial data set, document classification. That's an interesting one because like you could see that some documents, if it's like scientific related, you might see a lot of science words. And if it's like entertainment related, you might see different words. If it's there are different clusters of words that you notice, but there's a lot of overlap. So it could identify those clusters, and it may not know what this particular cluster of documents means, but it knows there's something there in common about them. And insurance fraud. IT alerts is another big one for network monitoring and like intrusion detection. If there's some set of activities that looks kind of suspicious, it might want to send an alert and say, look at this. Next slide, please. So how does Kmeans clustering actually work? Well, first you pick a number of clusters. So here we've picked like 3 clusters, and then you have to start by just guessing at the cluster centers. So it takes some guess and says maybe the cluster centers are here, here, and here. And then it's an iterative process. From there, it takes all the points that are closest. It just assigns each point to the nearest centroid. We're going to call the centers of these clusters, or baryocenter, or mean center of mass, sometimes in physics we call it. But it's basically just, ultimately you're trying to minimize the sum of the squares of the distances between these points and their centroids. And if it's not minimized, then you move the centroids to where it would be minimized. So that's the real center of mass of those points. Then you go back and say, oh, maybe now some points belong to this other cluster, and then you do it again. And you keep doing this iteratively. Next slide, please. So that's like a general technique that's in common for a lot of machine learning and MADlib algorithms, is that you initialize the problem, then you perform a bunch of steps, and then how do you know when to stop? When it converges, that's when you return the results. And convergence just means, in this case, the centroids, they'd be moving around, and once they stop moving a whole lot and they settle down to a particular spot, then it's done. Next slide. Next slide, please. Thanks. So this is like a simulation of how the centroids would move as you're actually training it. And then the prediction process would just, if you get a new point, it would tell you which cluster it belongs to, basically. Next slide. So this is not just Kmeans, but it's a recent version of Kmeans that we added. It's called Kmeans++ Auto. And it has a fancy way of picking the initial points. And then also, it allows, it automatically picks the best case. So a basic K-means algorithm, you would have to tell it, I think there's 3 clusters here, I think there's 4, find me the centers. But MADlib will actually pick the right K for you. If you give it a bunch of candidates, that's what this 4th argument here is, array 2, 3, 4, 5, 6. These are all the K values for it to try, and then it compares and tells you which the best one. And there's a couple ways of measuring which is the best one. Next slide, please. So one is called the silhouette method, and it's basically checking to see what is the, looking at the distances between, the average distance between the points and their center compared to the distance between those same points and the next closest center. So if you minimize that, that tends to work well. Next slide. And zooming in on the comparison between k equals 3 and k equals 4, these are histograms of all the different points in these clusters. And you see the black cluster really isn't handled well by k equals 3 choice. If that's 3 clusters, and the black cluster is very spread out, and those points are almost next to, they're almost halfway between the clusters they're assigned to and the next nearest ones. So that's why the black histogram doesn't look very good. And this dotted red line is not very far to the right, which would be a silhouette score of 1. And for k equals 4, it's much further to the right. Next slide. In terms of a formula, it's just subtracting this b minus a, where b is the average distance to nearest, basically what I was saying, and then you normalize it. There's also another method called the elbow method, and the elbow method is basically using the actual objective function, which, as I said, is like minimize the sum of the squares. But you can't just use that, because the more clusters you pick, like if you picked 100 clusters, the points would always be closer and closer to their centers. And so you can't just always pick the largest k. And so what happens is usually the objective function tends to decrease rapidly, and then at some point there's like an elbow where it starts decreasing more slowly, and that's generally the best k. Next slide. So this slide shows that in this case of 4 clusters, it identifies k equals 4 by either of these means. Next slide. And we've done scale testing on this Kmeans++, and it can scale very well with large data sets. So this is showing that basically, if you're looking at 10,000 rows, then it'll take 13 seconds, but 100,000 rows takes 100 seconds, 1 million rows takes 1,000 seconds. So it's scaling linearly with the data set. And all you need to do if you want to work on a larger data set is add more segments, add more hosts. Next slide. So now just a brief sneak preview of something we're currently working on, which is a more advanced clustering algorithm. Well, not necessarily more advanced, but just different. It tends to handle better weird shapes, whereas Kmeans tends to handle like circular shapes better. And it's based more on the notion of connectedness and also the density of the points. The DB and the DB scan stands for density-based clustering. You also need to pass it an additional input parameter, which is like a minimum distance between 2 points that would be considered them to be connected, like neighbors. And you also have a minimum number of points that a point needs to be like considered a core point. Next slide. And so it can handle shapes like this. Next, please. So if it identifies like these are the shapes, this is something Kmeans could not do because these are non-convex shapes. Next slide. So this is my final slide. It's just showing you what the basic dbScan algorithm is. It's basically, it just goes through all the points and then finds core points first, and then those are seeds for the clusters, and it grows them, and then it adds border points, and then it goes to the next cluster and grows them. And this works really well, but this is not a parallelized algorithm. What we're working on is making it efficient in parallel, and we have a really good plan. It'll make it more complicated, but one of the things that's really important is that this range query that it does to find the neighbors is really fast and efficient.
Thank you so much, Domino. I really, really loved your talk. You made it super easy to follow. It helps frame up the art of what's possible with Greenplum and Apache MADlib for me. So again, thank you so much for participating today.